now I can go home. So again, I'm Anusha Withana. We are from Saarland University. Me and my colleagues Daniel Groeger and Jürgen Steimle. We are going to talk about Tacttoo. Natural tactile sensation we have is one of the earliest developed and most important sensations we have in our body. It helps us to understand physical world around us and also do dexterous tasks and sometimes overcome disabilities and challenges we have. In other modalities, there are interfaces designed to preserve the natural senses. For example, in visual modality, there are see-through interfaces. In hearing, there are bone-conducting headsets that leave your natural hearing intact. So the question we want to ask is, what about in tactile domain? Can we create a feel-through interface? For example, can somebody feel the features on this tire through this mechanical interface? Well, with this one, the answer is simple, no. That's why we introduced Tacttoo. It is the first feel-through tactile interface, and also it is the thinnest tactile interface out there. It is 35 microns, which is about half the thickness of average human hair. And it also conforms nicely with small wrinkles we have on our skin. It is so thin and conformal, actually you cannot even feel it is there. The interesting thing is, in this really thin form factor, there is a dense array of individually controllable tact cells that can generate rich tactile sensation on skin. And it is easily customizable for different body locations. With these unique features, Tacttoo enables us to embed physical objects and also our own human body with virtual tactile sensations while preserving natural tactile features. And also it let us create private and subtle notifications and rich tactile sensation in virtual reality applications. Today, I'm going to talk about three main areas that are relevant to the contributions we make. First, I'm going to talk about how we fabricate Tacktoos. Secondly, about the safety features we implemented into the Electro Tactile interface. And finally, I'm going to show how well it works with the evaluations we conducted. Let's start with fabrication. So, to make it feel through, we wanted to make the Tacttoo interface extremely thin and conformal. Actually, our goal was to match or even do better than the impressive on-skin interfaces we have seen for sensing. To do that, we looked at different technologies available for tactile stimulation. We started with mechanical and electrostatic, ultrasound, and electrotactile. For our purpose, we decided electrotactile is the best candidate because it generates a sensation that is comparable with mechanical vibrations without using any rigid actuators. How electrotactile works is it directly stimulates our nerve stems in our skin using electrical pulses. But to do that, we have to deliver relatively high currents compared to sensing to our skin through exposed electrodes. This creates a big challenge in fabrication. As have shown by previous work in Kai, for example, recently, at these currents, electrodes deteriorate quite fast. So we have to figure out a way to create strong and consistent contact with skin using exposed electrodes. To do that, we propose a new fabrication approach by screen printing functional materials with different mechanical properties. In Tacttoo, to begin with, all the connective traces we print with P.PSS, which is a very thin and stretchable material. In contrast, for electrodes, we use silver, which is thick and rigid. And all the areas except for the electrodes we cover with, again, a thin insulating layer with adhesives. Now, you can clearly see here there is a nice contrast between the thickness and also the rigidity and the stretchability of materials. When we attach this on the skin, the thin P dot layers stretch and create tensile forces. These tensile forces in turn push the electrodes towards the skin. We call this a microspring mechanism. So this microspring mechanism helps us to create superior electrical contact with the skin. So how well does this work compared to previous work? Also, our own experiment with other material combinations and fabrication approaches. In this image, we show that even after 1 hour of continuous use, this microspring-based electrodes does not show any visual deterioration at all. And because we can print these taxels, actually, these microspring mechanisms, we can arrange them in custom designs to fit different body locations to generate versatile tactile feedback. So now that we have shown we can successfully fabricate Tacttoo devices, let's look at some of the safety features we consider and implemented. We see 3 important safety concerns arising with Tacttoo because we use relatively high voltages to activate nerve stems. First, compared to interfaces that you can touch and let go, in wearable devices like Tacttoo, people cannot let go. This is the natural response we do when we feel discomfort. Secondly, traditionally in electrotactile devices, they use a microcontroller-based control loop to regulate the current. But now we know microcontrollers can be quite buggy and they can be vulnerable to intruders. So we have to make sure that this wearable devices is safer than just without the microcontroller. Finally, we made the Tacttoo extremely thin and flexible, intentionally of course, but this means that it can be damaged under mechanical duress. So we have to make sure in case Tacttoo get damaged, not any of the electrical impulses does not leak into the surrounding environment. To address these problems, we introduced a 3-layer electrical safety architecture. First, we implement the closed-loop control with microcontrollers that has been proven to work for the control part. Second, we implement an overcurrent protection mechanism fully on hardware independent of the microcontroller. So in case microcontroller something goes wrong there, this part kicks in and disconnects all the circuits. Finally, we implement a leakage current protection mechanism so that if the Tacttoo get damaged, none of the electrical pulses leak into the surrounding. We believe this 3-layer architecture can be a reference design for any interface that use high voltages and current to make sure safety to the user. Now that we know we can fabricate tattoos and it is safe to use, let's look at how well these actually work. Here again, we wanted to answer 3 key questions. First, is it really feel through? Second, can it generate tactile sensation? And finally, is this thin structure durable enough as an interface? First, and probably the most important question is it really feel through? To answer this question, we conducted an experiment to see how Tacttoo affect the natural tactile acuity of our skin. We used a psychophysical experiment designed by Legge and others using ring charts to test the acuity of tactile sensation on skin. We considered 3 conditions. First, bare skin as the baseline, then Tacttoo, of course. Finally, we compared the effects of on the natural tactile acuity to the closest competitor or the state-of-the-art of tactile interfaces, which is about 100 microns thick. Results here show average acuity for 10 participants. Here, the lower the acuity, better you can feel, because that means you can feel finer variations. As you can see, Tacttoo performed significantly better than closest competitor or the state of the art. And also people can feel as good as, almost as good as bare skin with Tacttoo. So the next question is, can this feel-through structure actually generate virtual tactile sensation? To evaluate this, we again conducted a psychophysical experiment to figure out if the microspring mechanisms can deliver the necessary threshold of currents. Again, the results show for 10 users, all 10 users could feel tactile sensation. And the important thing here is the absolute thresholds we calculated is well below the maximum intensity we can deliver. So that means we have a good bandwidth to play around with. Finally, the durability. So the Tacttoo is extremely thin, so we wanted to make sure that it is durable over a long period, considerable period of time. We conducted an experiment, an 8-hour-long experiment in an office environment with 5 participants. Well, the gist of the results is basically all the Tacktoos survived the 8-hour working day. If you want to see more information about the experiments, you can please refer to the paper. Now we can say that we can successfully fabricate Tacktoos. They are safe to use and they perform well. Let's look at some of the unique applications Tacktoos enable. First, the feel-through properties of Tacttoo enable us to create interesting applications in tactile augmented reality. Going back to the original scenario that I showed here, now a designer can feel the natural rubbery texture on this tire through the Tacttoo interface, while we can simulate virtual tactile cues like engine vibrations using the taxels on the Tacttoo. Secondly, because Tacttoo does not need any instrumentation to the environment, we can simulate virtual tactile elements on our body. For example, we can create dynamic on-body landmarks where a user can navigate to a virtual button on the skin using existing physical tactile landmarks like veins and bones. And once you are on the button, you can feel the sensation of clicking through the taxels that create virtual tactile sensation. Finally, the dense array we have, dense taxel array we have in Tacttoo enable us to create rich tactile sensation on in virtual reality application. For instance, here a tree leaf or a stem or a sharp object can be rendered with a single taxel, while larger features like the stem of the tree can be simulated by activating multiple taxels simultaneously. In conclusion, today we introduced Tacttoo, a thin and feel-through tattoo for on-skin tactile output. It is the thinnest tactile interface out there, and it is the first feel-through tactile interface. We introduced the fabrication methods, safety architecture, and also the results from our evaluation showing how well it works. And finally, we introduced interactive applications in tactile augmented reality, dynamic on-body landmarks, and tactile feedback for virtual reality applications. Thank you very much.
So before we go for questions, let me just remind everybody that you can vote for the best talks. So there's ballot boxes outside. You can dump one of your tickets in there and vote for the presenters that are here this morning. Okay, now I open the floor for questions.
I'm Buntaro Shizuki from University of Tsukuba in Japan. Cool work. My question is, what about the robustness of your system for humidity or water? I mean, I'm interested in, does Tacttoo work underwater?
That we haven't tested for obvious reasons. But I think it is a matter of, well, let me talk about humidity, for example. If the concern is about the resistance, because skin resistance changes and this could affect the sensation. We use a current control mechanism so that the changes in skin resistance really doesn't affect. For example, if you put Tacttoo in water, it is not going to electrocute you or do something harmful, but it might affect the materials and it might dissolve. But I think this is also a matter of figuring out innovative ways to fabricate, make it water resistant. So it is a material thing, more about materials, I think.
Okay. Thank you.
Thank you.
Yeah. Thank you. Juan Zarate from ETH and EPFL, Switzerland. I had the chance to test it yesterday. It was pretty cool, the demo as well. I have two questions. First is, what is the center-to-center distance? And if you have explored resolutions issues. And the second one is, what is the comment of the users about how the people naturally associate this sensation to something they everyday touch?
Right. So the first question, the distance between taxels, we use 4 millimeters because this is 4 millimeters for the finger pad. This is our tactile discrimination threshold, special discrimination threshold for electrotactile sensation. So this is the highest density we can go for. The second question, how people feel about sensation, it depends. So even in the demonstration yesterday, some people felt it is strong, some people felt it is too weak. So to get it to really work, you have to calibrate the system. Once you do that, people feel it as vibrations, basically. But if it is too strong, people feel it as needles pinching. So this is the kind of like spectrum that we see in terms of sensation.
Gregory Abau, Georgia Tech. Excellent talk.
Thank you.
Two quick questions. One, is there any reason to believe there's a limit to the number of taxels you can have? And two, have you tried this for people to read Braille?
Right. The first question is how many taxels or the limitations. I don't think there is a theoretical limitation, but there can be practical limitations because if you... Okay, you cannot say it, but it is a matter of how we can fabricate these things together and how we can connect them individually. So this can be a limiting factor. The second question is, no, we haven't tried, but we would love to try it with somebody with, because of course they have, the people with challenges has heightened sense, and it would be fantastic to try it, but we haven't, unfortunately.
So, hi, Yongbo Shim from KAIST. Very interesting work.
Thank you.
I was just curious about how strong the effect could be, like, because I couldn't try the demo last night. So, like, compared to the real physically vibrated motors, how strong you could generate the vibration?
So, in electrotactile, the actual dynamic range that we can change the intensity is limited. So you cannot have kind of a wider dynamic range like in mechanical sensation. But you can clearly feel it. So it is, I would say it is a matter of actually controlling it to the level that it is not too intense. Because so whole calibration process is to make sure that it is not too intense. So you can feel it distinctly. But the actual dynamic range is quite narrow compared to mechanical.
I see.
But the sensation is comparable with mechanical.
Okay, thank you.
Thank you.
Final question, is it possible we could just take that
Yeah.
off? Okay, one more.
Oh, okay. Hi, Santiago Alfaro from Intel Corporation. Have you thought of inverting this whole system and using as a sensing mechanism?
We have. We cannot really give any concrete information at this point because we have to test it. But we have implemented sensing on top of this, like for example touch sensing. So you can stack these layers together so that you can integrate touch and you can integrate visual output together with tactile output. Yeah. So that is the flexibility of this DIY fabrication approach. So you can put things together I think previous work from the group shows visual output and very versatile sensing in similar interfaces. So in this project, we just want to break through to the tactile domain. Yeah. Thank you.
Thank you. One more note, Anusha is a newly minted assistant professor at University of Sydney in Australia, and he's looking for master's students and PhD students. So if you're interested in this work, go and approach him. That's it for this session. Thank you very much for your time.